field. And then what you do is you get this communication structure going, which is like a wavefront computation, except now it's going through the unstructured mesh, where each cluster is receiving an aggregate of inputs from one of its predecessor clusters. This is specified by a graph. So you have really collections and a graph data structure. And we figured if we could understand how to do this, the HPC people will relate to it, and we'll have the right foundations for non-numeric programming as well, as one example. Don't have time to go through all the detail, the initialization, but just to sort of give you the idea, and later on I'll give you a glimpse of the kind of MPI code that would be needed to do this. What we are saying over here is the notion of clock is that you have a phase and a high-level time step in your program. Sorry, I don't have a pointer here, but it says this whole region of code is done in one phase, and when you say next C, then you advance to the next phase. Oh, great, thank you. So that's kind of like the barrier, but except it's tied to this clock. And then at the outer level, we can iterate across the nodes. Later on, I'll also show you an example where if you want more control over the performance, you can actually iterate over the places. So you iterate over each cluster and then iterate across the nodes within each cluster. And then you iterate over the sweeps. It turns out that there are multiple sweeps you can have. Receive inputs. To receive inputs, this is the you have asynchronous operations to receive input basically on these input channels. Now there's an interesting choice over here as to how you want to synchronize on those receives. You could force each one of those to be synchronous, which would be really limiting. You could have a clock-like barrier over here which says, tell me when I'm done with all of them. Or you can be even more lazy and push it down as a future into the consumer. And that's something that's going to be one of the dimensions of performance tuning. But these are the mechanisms available. And you send the output. What's interesting is that these constructs can kind of map to the different levels of hierarchical parallelism that I alluded to earlier. So this can be spread out across clusters. Here you can use SMPs, you can use SMTs, and then within the flux computation you can use coprocessors and vectors. So that's. And that might look kind of straightforward and natural, but this is the state of the art today as to how people, and actually this is not even for unstructured mesh. This is for just a simpler example where someone's doing a structured mesh with just +1 and -1. And what's going on over here is that there's a lot of intermingling of the APIs of the programming model with the code that you write. So trying to do type analysis, this is C, you can see a lot of the address operators. You've lost all type information. You make a mistake in any one of these addresses, you can completely corrupt the integrity of your data structures. And there are many things that can go wrong in this coordination. Okay, just another, I alluded earlier to atomic sections, so let's use a Java example to illustrate that. This is from SpecJBB. Here's one of the classes which, there are two methods that operate on the class, and each of these is declared as synchronized, and we know in Java that means that there's a lock associated with the object, and these methods will synchronize on it. It turns out, and Doug has many such good examples in his book as well, that these two methods don't interfere with each other. But for convenience, for other abstraction reasons, it was convenient to put them in the same class. What we are proposing is that you declare them as atomic and leave it to the implementation to decide how to implement them. In particular, the implementation could decide to split the lock into two locks. Or in some cases, if it's a simple enough method, you could also use transaction memory or other kinds of hardware support that people are proposing. So we feel that this is well within the reach of optimization techniques in the time frame we're looking at. Conditional atomic sections, the idea of which, so this is continuing with SpecJBB, there's a lot of hand rolling, and this is before your JSR talk, of people trying to implement barriers on their own. And you can see a lot of the, wait notify constructs and keeping track of your own count and figuring out if everyone's reached the barrier, etc. I guess if you really want a barrier, you could use a clock, but when we were trying to stay faithful to this notion of trying to count the threads. So this, the conditional atomic section says you wait for this condition, and when it becomes true, you enter the atomic section. And what the semantics guarantees, and this is probably the most challenging construct in the language, is that you want this combination, this condition becoming true in the body of the atomic section will together be atomic. And that's, and we are looking at now special idioms of those where we could do special cases of those more efficiently. How am I doing for time?
You have 4 minutes.
4 minutes, okay. So along with the language, we are starting work. I'll tell you about status. We've got a compilation framework that we're starting to plan and build. We'll have a front end. We have class files. In the initial incarnation and our initial prototype, an extend class file will really basically be a Java class file with some extra metadata or attributes. We have some infrastructure in IBM research that we're going to use for static optimizations. The virtual machine with the continuous program optimization that Evelyn mentioned, targeting this kind of hierarchical parallelism and using profile feedback from all the layers, which is the hardware, the operating system, and the virtual machine for both the static and the dynamic optimizers, and also using hardware info. Another exercise that was interesting was we looked at different programming paradigms and looked at how they could be expressed in extend. And it turns out that you can actually think of something like message passing as an extend program with but some limited assumptions. There's one activity per place. Each node becomes a different place, and essentially you don't have any partition global access. All the data is placed local, and messages turn into asynchronous operations, and so on. You can look at shared virtual memory, DSM, UMA as different special cases. So from that, we feel there's an opportunity to leverage a lot of past work on optimization for these idioms, but in a common framework. And we already are aware that aggregating these asynchronous operations is going to be one of the key optimizations here. Probably don't have time to get into it, but at the extend level, you can express many optimizations just to show you how much control the programmer can have over performance. So a very simple example, array copy, which can get complicated if the source and destination arrays have different distributions. This is an indicator of how we are building on parametric types as in Java 1.5, where things like the element type and the distributions can all be parameters. And one way is to you just say that you want to do this copy with asynchronous operation. The problem over here is you have one asynchronous operation for each read and one for each store, so you're spawning a lot of activities. The second is you could choose to optimize this, either the compiler or the user, and you could just iterate over the places, and then in parallel, and then sequentially iterate over all the elements in the place. This is a restriction, and here it talks about this place. And this, I'm not advocating that the user write this kind of code, but it's nice that this kind of transformation can be done as a high-level transformation. Would say you iterate over each of the destination places, and then you iterate over all the source places and aggregate the data that you receive. So aggregation can be expressed. Status, we've started work on a prototype that's going to be functional, that we expect to have available by end January, just for testing out the language constructs, not for performance. We're going to do productivity experiments, trying to compare them with other programming models. And by end of next year, we plan to have a prototype that will show some interesting performance results as well. I alluded to this. We believe existing programming models can be migrated to extend. So one approach could be to start with a simple migration, and then start using the additional features of extend once you've got the migration going. There are implementation challenges. I mean, we will have our work cut out for till 2010, but I think this is all in the realm of feasibility. So to conclude, I think these large-scale systems, what I talked about, the hardware trends, they pose some unique challenges. I tried to share with you our overall approach in Perks and the extend language. We're really going to use applications and productivity studies, and these are real, productivity studies with human subjects. You get to implement the same code in in your current programming model in Xten and learn from that. And in future work, and didn't have time to talk about this today. This relates to other work that we do at research. We're going to look at trying to integrate this in other domains. The XML domain, we have a separate project called XJ that's looking at that without the concurrency aspect. We see those as two orthogonal issues. There might be an interesting merge. BPEL, the asynchronous operations over here, could integrate well with asynchronous operations with BPEL and so on. And finally, the goal of all of this is to see if once we've learned what the right technical approach is can we have a community effort to form a consensus on what the language should be so that we can be prepared for it in the 2010 timeframe.
-1 question?
Okay.
Excellent. Thank you.
Make a comment. In my NGS program, I've been telling people they should move beyond SPMD, and I'm glad Xten comes again from OEM.